This is Kosuke Kikuchi, Application Engineer at NAC Image Technology. Today, I will explain special optical technology for visualizing plasma. This is the agenda for my presentation. At first, I will introduce the plasma visualization and case study and a special optical system for visualizing plasma. Finally, I will introduce multi-wavelength measurement using special optical system. From now, I will introduce the required frame rate and appropriate high-speed camera for visualizing plasma and discharges. To visualize plasma, we must first consider how clearly we observe the phenomenon, its time resolution. Visualizing phenomenon requires equipment like high-speed cameras. Here is the relationship between the various phenomena and the required frame rate. Generally, almost all phenomena is usually shot at 1000 frames per sec to 10,000 frames per sec. On the other hand, plasma phenomena are extremely high-speed events. So measurements at the microsecond and nanosecond level like 100,000 frames per sec to 100 million frames per sec were required. Additionally, to visualize the plasma phenomena occurring instantly within the ultra-short durations, image intensifier or ICCD might be required. Our high-speed camera features a lineup ranging from hundreds to 1 billion frames per second. Our latest camera, HS1, has high-speed performance exceeding 1 megapixel at 100,000 frames per sec. Additionally, we develop and manufacture the Ultra-NAC Tau in our domestic factory. Combining our optical design technology with custom sensors, it enables ultra-high-speed capture of the 12 frames at intervals as short as 1 nanosec. I will introduce examples of the plasma and electrical discharges. This is the HS1, a high-end high-speed camera. It captures 54,000 frames per sec at 1.14 megapixels, and with its performance enhancing boost mode, it can shoot at up to the 150,000 frames per sec. ISO sensitivity is also exceptionally high at 100,000 in monochrome, making it suitable for visualizing plasma phenomena. This is an example of the plasma fusion imaging. Using the HS1 camera as the Quest spherical tokamak experiment device, which generates plasma and confine it magnetically with the spherical tokamak, we are able to capture images at 45,000 frames per sec and observe the details of the plasma behavior. Due to the significant effect of strong magnetic field and high voltage noise generated by the plasma, the camera is housed in the sealed box and observed through the visualization window. This is another plasma phenomenon captured by the Quest. The camera was a high-definition, merge-head model, MCAM shooting at 2000 frames per sec. Shooting in color also allowed us to capture the color information of the plasma gas. Furthermore, because the MCAM is compatible with Micro Four Thirds mounts, lens remote control is possible remotely by a tablet operation. This sample video captures the behavior of the plasma generated and accelerated and collide and merge from opposite side by a spherical torus fusion experiment device. It was color filmed at 100,000 to the 500,000 frames per sec using the UltraCam. By varying the gas mixture ratio and with argon helium or hydrogen, the emission spectrum changes, and alterations in the plasma generation process and the collision characteristics were observed. Additionally, research is in progress on technology to transport plasma generated by the nuclear fusion using the magnetic field. This sample video was captured at 400,000 to the 1 million frames per second using the ultracam. Arc discharge during welding is one of the plasma behavior. Using the ACS1, we captured observation of the cathode points generated on the base material surface during the MIG welding at 50,000 frames per second. The drop migration process is clearly captured. A key feature of the monochrome camera is its sensor sensitivity extending into the near-infrared regions around 1000 nanometer. By using the near-infrared bandpass filter, the camera effectively cut out the strong visible light emitted by the arc discharge. This allows the wire droplet transfer within the arc to be observed more clearly than with its color imaging. We observe the cathode spot generated on the base metal surface as the instant TIG welding switches from the AC to DC. Using the ACS1 color camera at 100,000 frames per second, the high pixel count and sensitivity allowed us to clearly see electrons moving around the molten pool immediately after current flow began. The color camera enabled us to observe color information of the base metal and tungsten electrode load. Next, I will introduce visualization example of the using UltraNAC series of ultra-high-speed cameras. There are two models. Ultra Neo achieves up to 200 million frames per second, and Ultra Tau achieves up to 1 billion frames per second. While the number of the frames recorded is 24, it enables sequential observation of the ultra-high-speed phenomena occurring in the nanosecond range, such as discharge and plasma. Custom models sensitive to the ultraviolet light are also available. This is a shooting video about the generation process of atmospheric pressure plasma by laser breakdown using UltraNAC Neo at 100 million frames per second. The upper part of the screen shows direct imaging of the plasma emission, while the lower part shows shadow graph imaging of the shock wave behavior with cutting the emission with a bandpass filter. Additionally, some laser breakdown phenomena occur too rapidly even at 10 nanosecond intervals, requiring the higher temporal resolution. We will introduce this case study to the next slide. This is laser ignition plug development, showing the generation process of the plasma created by the pulse laser, captured at 1 billion frames per second using UltraNAC Tau. This represents the world's highest level of the imaging speed achievable for the continuous sequences. Laser ignition utilizes thermal plasma formed by the laser breakdown, enabling ignition at any point by adjusting the lens focal position. This allows multi-point ignition at location distance from the combustion wall, particularly advantageous for the large war engines used in power generation. This is an example of the streamer discharge occurring during the ignition in the automobile spark plug, captured at 100 million frames per second using UltraNAC Neo. During the initial discharge phase, a streamer discharge spread like branches, gradually generating into the single arc discharge. Observing the temporal sequence at the nanosecond level reveals how the discharge phenomenon expands. HID lamp discharge, also used in the automobile headlight, is another plasma phenomenon. This is a discharge precursor phenomenon captured at 200 million FP using the ultra-NUC-NEO. To capture image through the visualization window at the top of the vacuum chamber, a dedicated vertical inverted micro-positioning stage allows its fine-tuning of the position to align with the observation area. This case study evaluated the impact of the natural lightning strikes on the CFRP materials by measuring discharge phenomena during the lightning strike test. Ultra-NUC-NEO captured 100 million FP and ACS1 shot at 100,000 FP. Additionally, application of the new plasma-based film deposition technologies are also being explored. Here the plasma deposition process was captured in color at 1 million FP using the ultracam. This provides insight into the behavior of the rotating plasma and the color information of the plasma gas. We capture plasma film formation inside a medical fiber tube, simulating an artificial blood vessel at 100,000 to 200,000 FP using the ACS1. The movement of the spherical plasma traveling through the fiber was successfully recorded. This is research on the plasma jet propulsion. Observing the ionization wavefront driven by the 300 kW microwave discharge. It was filmed at 75,000 FP using the ACS1. This is an example of observing the surface discharge of the plasma actuator, a plasma-based airflow control device in the ultraviolet region. It was captured at 10,000 FP using ACS1 and image intensifier. There is a process for generating metal powder for 3D metal additive manufacturing using plasma. A metal rod is rotated and melted by plasma, while powder is ejected by the centrifugal force. This was captured at 100,000 FP using the ACS1. By cutting out the plasma emission, we are able to capture the powder generation process. At the next section, I will introduce a specialized optical system for visualizing plasma phenomena. First, I will introduce the two-color splitter optical system. The two-color splitter optical system enables simultaneous measurement of the two wavelengths by splitting and projecting image on different wavelengths onto the same sensor. It features a compact design and can be easily connected to any camera type. The principle of the two-color splitter optical system is as follows. Incident light is split by the dichroic mirror or half mirror, then reflected by the mirror and imaged on the camera sensor after passing through the two wavelengths bandpass filter. The lens mount on the subject side is C mount, while the camera mount on the sensor side is F mount. Also, the design allows for the arbitrary wavelength selection by replacing the filters. Commercially available 25 mm diameter filters can be attached, and the filters can be easily changed by unscrewing the filter holder. A key feature of the two-color splitter optical system is its built-in alignment chart, enabling the positioning adjustment of the two dual wavelengths imaged regardless of the same sensor size. Lower the chart, move the internal mirror and left-right mask, and adjust the center position of the left and right image to match the pixel count. On-site adjustment takes just 30 minutes. Application of the two-color splitter optical system includes the temperature analysis of the diesel combustion flames and the temperature analysis of the molten metal in processes such as welding and metal additive manufacturing using the two-color method. Additionally, simultaneous multi-wavelength measurement of the combustion flames sometimes involves measuring both the ultraviolet emission of the OH radical and the visible light. We also plan to apply this technology to spectroscopic measurement of the plasma in the future. Next, I will introduce the alpha prism. This prism optical system divides the image entering through the input window into the four parts using the internal optical system with a half mirror or dichroic mirrors, and projected multiple images onto the same sensor surface. By attaching separate bandpass filter to the output window, simultaneous measurement of the specific wavelengths is possible. The alpha prism features an ultra-compact design that fits between the lens and the camera sensor, enabling it to be built into the camera F-mount adapter. So simply swapping the mount allows this switching between the standard camera photography and the four wavelength photography. As an application of the alpha prism, it can meet requirements such as the two-color temperature analysis, simultaneous multi-wavelength measurement in the plasma and combustion, and polarization measurement. Furthermore, as a custom solution, it can be designed to match the sensor size of the camera and offer flexibility in wavelengths, splitting according to the purposes. It enables splitting into multiple wavelengths using the dichroic mirrors, or multi-splitting within the same wavelength range using the half mirrors. While its purpose differs from the plasma imaging, custom-made bathscope can also be manufactured. It has become an essential tool for visual measurement inside the actual engine cylinders. Key features of our bathscope include a custom design for heat-resistant and pressure-resistant applications, and compatibility across a broad wavelength range from ultraviolet to infrared. It is a domestic product design, machined and manufactured at the Yokohama factory. I will introduce a multi-wavelength measurement using the special optical system. First, I'd like to introduce the metal temperature analysis using the two-color splitter optical system. At Professor Kikuchi's laboratory at the University of Hyogo, we capture the temperature rise of the metal subjected to the high-speed impact by the plasma gun. We capture the rapid temperature rise during the collision between the plasma ejected from the plasma gun and the metal at 100,000 frames per second, and perform the temperature analysis using the two-color temperature analysis software, SAMIAS. The target metals are titanium on the left and aluminum on the right. This research aims to investigate the effect of the plasma on the wall materials in the next generation plasma fusion device like ITER. I'd like to introduce the spectroscopic measurement of the plasma collision mergers conducted by Professor Tanabe at the University of Tokyo. While utilizing the UltraCam and ACS1 for plasma collision merger measurements, simultaneous visualization with the high-speed camera is performed alongside connecting multiple imaging fibers to a spectrograph, enabling to the dimensional spectroscopic image capture in the single exposure using the ICCD. Next, this is an example of the measurement taken by the Plasma Research Center, University of Tsukuba, during the non-contact plasma experiment in the gamma-10 using the alpha prism attached to the HS1 by simultaneously measuring the spatio-polar distribution across 4 wavelengths. This approach contributes to elucidating the reaction processes between the plasma and gas. This is an example of using HS1 and alpha prism in the Professor Tonegawa plasma experiment at Tokai University. Observations were made using the two-dimensional Barman series diverter simulation device for the non-contact plasma. Measurements were taken at 3 wavelengths. This is from Professor Masahiro Kobayashi's group at the National Institute for Fusion Science and showing the non-contact plasma state observation using the TBD2 plasma experiment device. Reducing the thermal load of the plasma on reactor walls is crucial for fusion reactors. Therefore, research is being conducted on non-contact plasma, which reduces the plasma temperature near solid walls via radiactive cooling and extinguishes the plasma. By imaging the 4-branch image from the alpha prism onto the image intensifier tube UVI using the tandem optical system and applying the 4-branch light with the image intensifier, the emission spectrum of the hydrogen plasma can be measured at the high speed across 4 wavelengths using the SS1. The video shows the state during the transition from contact plasma to the non-contact plasma. This is another example of observing the state of the contact plasma using the TBD2 plasma experiment system. Observed through the two-color splitter optical system. Using the newly designed two-color splitter optical system compatible with the HS1 sensor size and HS1 itself, simultaneous observation at the 2 wavelengths 410 and 434 nanometer was performed. Although the emission from the hydrogen plasma is stark, HS1 can measure at 1000 frames per second even without an intensifier. Finally, let me introduce our follow-up system. We are not only engaged in the camera sales, but also provide these services: special order consulting, comprehensive support and maintenance, and training for the overseas distributors. Thank you for your attention.